Hello, in this video I will go over properties of vectors, perform basic vector operations, determine if a vector is a linear combination of another vector. I will determine if a vector is within the span, write an equivalent system of equation for a given vector equation, and finally construct a vector as a linear combination of a set of a given vector. So yeah, let's talk about what is a vector. So a vector is a quantity with both magnitude, length, and direction. So yeah, a vector is a quantity with both magnitude, length, and direction. A vector can be denoted using a bold type U or with an arrow U. So you can write it as, yeah, exactly like I said, back like this, or you could just say U. I prefer this. Okay, two vectors are equivalent if they have the same size and direction and only differ in position. So example, vector U is equal to vector V. So wait, an example could be vector U could be expressed as like this. Later on, we're going to transpose it, and it will be also be expressed as one like this. So you've probably seen this as a coordinate. You've probably seen 1, 2 as a coordinate. It's almost the same. The coordinate 1, 2 is the same thing as a vector. You have the x direction and the y direction. So you can write it as this, or you can write it as a transpose like this. Multiplying vector by scalar will change the magnitude, but not the direction, uh, unless the scalar is negative. So, for example, vector u, and then if you multiply by vector u by the scalar 1/2, it's going to look smaller. If you multiply the vector by the scalar 2, it's going to look longer, right? Multiplying by negative scalar will cause a vector to point in the opposite direction, right? So, for example, if you multiplied vector u by negative 2u, it's going to go in the opposite direction. So, yeah. When we add two vectors called vector addition, it forms the diagonal of a parallelogram. Okay. So just note when you're adding or subtracting vectors, they have to be in the same size. Otherwise, you can't add or subtract. So let's look about what's really happening when you add vector u, vector v. So let's pretend this is vector u, and then this is vector v. And when you add vector u plus v, you get a new vector. So let's pretend vector u was, I don't know, 0, 1. And vector v was 3, 0. If you add vector u plus vector v, you're going to get a new vector, and you just basically add all the x's and all the y's. So your x's are 0 plus 3, and then your y's are 1 plus 0. You put it all together, you get 0 plus 3, which is 3. 1 plus 0 is 1. And then you get vector 3, 1. Okay, so they have to be the same size when you're adding or subtracting vectors. So vector space and column vectors, any coordinates x, y can be as a vector, sometimes called a column transpose. So it's just transposing. So like I said in the previous example, let's pretend this was 3, 1. You can rewrite this as a transpose vector. So you kind of like, it would be expressed as You can 3 comma 1. Okay. And then you can also have a three-dimensional vector. I'm not going to do too much about three-dimensionals. You'll learn this more in Calculus 3. So for example, the vector x comma y comma z can be written as x, y, z in the plane r cubed. Okay, so let's briefly talk about linear combination and expanding. So I'll talk about it again later on as the lecture goes on, but linear combination and expanding might be difficult to understand at first, but if you just follow the scenario, this problem will make better sense. Think of planet Earth or traveling across the world. Let's say you reside in California and you want to visit the United Kingdom, right? How do you do that? Well, there's a few options. You can, one, fly. Two, you can take a ship. Three, maybe drive later in the future, maybe. Or you can train later in the future, right? Maybe they will uh, find an underground tunnel or something. Maybe you can walk, run, bike later in the future. But right now, I think the best way would be fly and ship, right? Because you have to pass the ocean, right? So you can do all those transportation, but at the end of the day, you will eventually end up in the United Kingdom. You can think of the transportation like flying, boating, etc., as a linear combination, and your destination would be the United Kingdom as the span. In linear algebra, we will find the linear combination that goes with this specific span. Or we will be given a specific linear combination to see if it works with the span. So also note, you cannot have a scalar linear combination. So what that means is running and walking, they both give you the same destination. Since they're both almost the same thing, or known as a scalar linear combination, we can't have that in linear algebra. So if they're almost the same thing, they won't work. Okay, so vector equation. A matrix is a generalization of vector where we rearrange numbers in both rows and columns, n by n. But when we view vectors as a matrix, we rotate or transpose them as an n-dimensional vector as an n by 1 column matrix or a column vector. So for example, vector v is 1 comma 3. And then let's say you want to transpose it as a matrix vector, it would be matrix 1 3. And as you can see, this now will be 2 rows by 1 column. And the same thing with the three-dimensional. So vector u is a three-dimensional vector. It would be expressed as -1 comma 5 comma 4. That would be transposed as -1 5 and 4. An example would be vector x. It would be like n by 1. Basically, you just kind of vertically twist it around, if that makes sense. Algebraic properties and concepts. To find the sum of two vectors, they must be the same size. So that applies to adding and subtracting vectors. They have to be the same size. And you add the corresponding entries. To find the scalar multiple of vector, you simply multiply each entry by the same constant. So here are some properties. Vector u plus vector v. That could also be expressed as vector v plus vector u. And when you're adding and subtracting, they must be the same size. Here you have vector u plus vector v multiplied by a scalar c. So all you got to do is multiply that scalar, FOIL it out, and that's also known as the associative property. And this one, vector u plus vector v plus w, you can switch the orders around and you'll get the same answer. This is also the, I forget what property that is. I I think it's what is it, the association property? It's the same thing, right? You can switch the orders around and you'll still get the same answer. And rule 4 is very similar to rule 2. You gotta just FOIL out this u, and you'll get your new vector. And then if you vector u plus vector 0, we'll just give you vector u. And then rule 6, if you have a scalar c, go ahead and FOIL that out. Rule 7, vector u plus negative vector u will give you a vector of 0. And one vector u is vector u. Okay, so let's do some examples. So let's say you have vector u, which is 2 comma negative 7, and vector v is 1 comma 4. Part A says find vector 4 times vector u. So 4 is a scalar. So all you got to do is you can write it if you want. You can rewrite vector u as a transpose vector. So this would be 2 comma negative 7. And then all you got to do is FOIL out the scalar 4. So FOIL that 4 out, so that would be 4 times 2 is 8. And then 4 times negative 7 is negative 28. Okay, so that is vector for you. Vector v, letter b. This is like a -1 scalar, -1 times vector v plus 3 times vector u. So what I'll do is rewrite vector v as a transpose. So it would be 1 comma 4. And you have a -1 here, plus 3 times vector u. I'm going to rewrite vector u as a transpose, so that's 2 comma negative 7. Then what I would do is FOIL out the scalars. So -1 times 1 is -1. -1 times 4 is -4. Plus 3 times 2 is 6. 3 times -7 is -21. Okay, so now we're adding vectors. So they are the same size, so you can add them. So just do them across. What's -1 plus 6? +5. What's -4 and -21? -25. Yep, I'm just double checking. Yeah, that's correct. Okay, vector 0 is just going to be 0, 0. So yeah, now let's do a linear combination. So linear combination is an expression constructed from a set of terms by multiplying each term by a constant and adding the results. So let's do an example. Given x and y, the linear combination would be ax plus by, and a and b are the constants. So let's do an example. So what does this mean for vector? So what does this mean for vectors? So you have vector 1, which is 1, 2, 3. Vector 2 is 3, 5, 1. And vector 3 is 0, 0, 8. If you add them up, just because you can add them, they're the same size. So 1 plus 3 plus 0 is 4. 2 plus 5 is 7 plus 0 is 7. 3 plus 1 is 4 plus 8 is 12. Okay. Let's do another example. So let's say you have vector 3 comma 1 and vector v is 1 comma 5. What happens when you add vector u plus vector v? Well, check first if you can add them. Can we? Yes, because they are the same size. They're both 2 by 1. So u plus v, vector u plus vector v is 4 comma 6. And if you want to see graphically, how do you plot vector v? It's kind of like a coordinate. So 3 is like your x, 1 is like your y. So if you plot 3 comma 1, you put a dot here, and then from the origin, draw a straight line or an arrow from the point. Right? So this would be vector u. Vector v, this one is your x, this 5 is your y. So if you plot that point, 1 comma 5 would be right here. And then all you got to do is put connect a dot from the origin from the point 1 comma 5. And then vector u plus vector v would be 4 comma 6 because you just add them up across the row. So 3 plus 1 is 4, 1 plus 5 is 6. So what you do is plot the point 4 comma 6 and then always start connect the dots from the origin, right? So this would be vector u plus vector v. Okay. If vector 1 and vector 2 and vector v are in Rn, n comma 1 column matrix, then the set of all linear combination of vector 1, vector 2, vector 2, vector vp is denoted by the span vector 1, vector 2, vp. In other words, the span is the collection of vectors that can be written in the form of cv1, c2, v2, cp, vd, and the amount to us asking whether the vector equation has a solution. So what this really means is going back to the scenario. Remember, if you want to travel across the world, you can either fly, ship, walk, etc. But will it still give you across the world, right? Or if you want to travel from California to the UK, you can basically fly or ship, but either way, it's going to give you the same destination. So that's what this linear combination means. But yeah, so like we said, think of the planet Earth. How do you travel around the world? 3 options: walk, swim, drive, ship, etc. Yeah, so C1 would be the linear combination, and then the world would be the span. Okay, so yeah, we can have different variation, but still have one outcome. So let's do an example. Let's say vector v1 or v naught is 2 comma 2 1, and vector v2 is negative 2 comma 2. Express each of the following as a linear combination of v1 and v2. So let's look at part A. How would I do this one? So basically, we need to find the linear, express each of the following as a linear combination. So what this really means is we have vector u 0, comma 3. So we got to find a v1 plus b v2 gives you vector u. So basically, we're trying to find the scalar a and b, right? Because that is your linear combination. So what I'm going to do is write it as a, and then oh, and then we know that v1 is 2 comma 1, so it would be a 2 comma 1 plus my unknown, or my b. I don't know what my b is. And then my vector 2 is negative 2 comma 2. And then that equals to vector u 0 comma 3. Okay, so uh, what we have to do is set it up as a matrix. So wait, what this really means is vector v1 plus vector v2 gives you vector u. So that means u is allowed to be in the span. So what we're going to do is set it up like I set it up like this. We're going to make it as a consistent matrix. So what that means is we're going to set it up like this: 2, 1, -2, 2, and then straight line because it has to equal to the u vector, which is 0, 3. And then what our goal is to make this matrix look like this, right? 1, 0, 0, 1, and then number here, and then number there. That's our goal. So can we do this? Let's see. So if I want to make this 1 into a 0. I don't worry about these twos here because you can always multiply it by a scalar. So first focus on this 1. I want to make that to 0. So what that means is I'm going to have to, so that's technically row 2. To do that, I think I'm going to have to multiply -1 times row 1 plus 2 times row 2. And then that'll give us my new row 2. Okay, so when I do that work, the first number on row 2 would be 0, which is what I want. The second number would be 6, and then the third number would be 6. And then here, this stays the same, so you have 2, -2, 0, etc. Okay, then what I'm going to do next is, what would I do next? Maybe I'll just make, I think to make life easier, let's make this 2, -2 into 1s. So how would I do that? I would have to multiply it by the scalar 1/2. And then let's make this 6 and 6 1, and I can do that. I can multiply scalars more than once. So row 1 would be 1/2 row 1, and then the second one would be row 2, and then just multiply the scalar 1, 6. So when you do all that, 2 times 1/2 is 1, -2 times 1/2 is -1, and then this would be 0, and then 0 times 1, 6 is 0, 6 times 1, 6 is 1, and then 6 times 1, 6 is 1. Okay, and then now I want to make this -1 into a 0. So that's technically messing with row 1. To do that, I would have to multiply, I'm going to have to multiply row 2 by row 2 plus row 1. So that would give me 1, 0, straight line, and then this is 1, and then this is going to be 0, 1, and 1. Okay, now we got it the way we wanted. So this is like your A1, and then this is your B. So that means B equals to 1, and then A equals to 1. So I think we found our answer. So express choose the following as linear combination. So our limited combination is, so yeah, we found our A, which is 1, and then our B is 1. So let's check. Does this, let's see if, if this is true. So if our A is 1, and then we're going to multiply by the vector 2 comma 1, and then if our B is 1, multiply by the vector negative 2 comma 2, and then that gives you the vector 0 comma 3. So if I multiply this out, 1 times 2, that's 2. 1 times 1 is 1. And then if I multiply this one, this would be negative 2. 2 gives you, does this give you a 0, vector 0 and 3? So 2 plus negative 2 is 0. 1 plus 2 is 3. Yes, it does. So we just, we found it. Our, yeah, our linear combination is 1. All right, for the A value is 1, and then our B is 1. So that's how you find your linear combination. You set it as a matrix, simplify it to this, and then find your A and B. I mean, will it sometimes give you, this is always possible? No. Then there would be no linear combination. When would it be impossible? Let's say if this one was like 0, that would be a false statement because 0 does not equal to 1. So that means there's no linear combination. Okay, let's do B. So this time W is going to be vector negative 4 comma 1. So the A, the V1, V2 is 2 and the same, V1. Okay, so in B, the only difference is my vector W is equal to negative 4 comma 1. So instead of equaling it to 0 comma 3, we're going to equal it to negative 4 comma 1. So what we're doing is basically setting it up like this. A V1 plus B V2 gives you vector W, not U. Right? So we got to figure out A. So A would be, we don't know, and then vector V1 is 2 comma 1. And then B, we don't know, vector V2 is negative 2 comma 2. And then vector W is negative 4 comma 1. Okay, so how would we do this? So just like the other one, you set it up as a matrix. So this would be, I mean, could we figure it out without a matrix? Could we? So what could we do? Can we get away with it without doing matrix? Yeah, I think we can. Maybe we can multiply the A. A could be positive 2, so 2 comma 2 comma 1, and then maybe B could be just 1. So if you FOIL this out, this would be 2 times 2 is 4, 2 times 1 is 2, and then this would be 1 times negative 2 is negative 2, 1 times 2 is 2. Add them up. Uh, that's not going to give you negative 4 comma 1. So that's not going to work. How about if I multiply A by negative 2, negative 2. So let's try negative 2. Negative 2 for A, so this would be 2 comma 1. And then maybe B is still 1. So negative 2 times 2 is negative 4. Negative 2 times 1 is negative 2. And then 1 times negative 2 is negative 2. And then 1 times 2 is 2. no. How about if a was -1? So if a was -1, that would be -1 times 2 comma 1, and then maybe b would be +1. -1 times 2 is -2. -1 times 1 is -1. 1 times -2 is -2. 1 times +2 is 2. Add them up. -2 plus -2 is -4. 2 plus -1 is 1. Perfect. So my a value will be -1, and my b value would be +1. So we could have got away with it without a matrix. Okay, what about c? Um, our new vector is 6 comma 6. So you would set it up as a v1 plus b v2, and then it's going to equal to 6 comma 6, right? So if we set it up, we got to figure out our a and our b. So a and our v1 is still the same, 2 comma 1, plus b. My v2 is -2 comma 2, and then it's going to equal to vector 6 comma 6. Okay. So can we solve it? 3. Maybe we can set a to 4. And then maybe we can set b just as 1. Let's see if this works. So this would be, if you FOIL out the scalar, 4 times 2 is 8. 4 times 1 is 4. And if you FOIL out the scalar 1, 1 times -2 is -2. 1 times 2 is 2. Add them up. 8 plus -2 is 6. 4 plus 2 is 6. Perfect, it works. So that means our a value is 4, and my b value is 1. Okay, next example, determine if vector v is a linear combination of a1, a2, and a3. So that means we have to figure out how would we set this up. We got to find out, we're going to set it as a matrix. Yeah, so what we're saying is we got to find the linear c1 times vector a1. So c1 is your linear combination, and then c2 would be your other linear combination for vector a2, and then c3 vector a3, right? And then that should give you your vector b. So how do we set it up? I'm going to just set it up as a matrix. So it's going to be, yeah, because it's too complex. Now we're dealing with 3 linear combinations, so I can't just come up with my head. So I'm just going to write it as a matrix. So this would be 1, -2, +2, 0, 5, and 5, 2, 0, 8, and then straight line. And then you have the coordinate -5, 11, -7. Okay, so what you would do is you're going to have to make, your goal is to make this 1, 0, 0, 1, 0. Maybe you don't have to, but you can make this into a 0 or a number. And then, actually, let's make this 0. And then your goal is to make this 1, 0, 0, and then number, number, and number. Okay, so let's see. That's our goal. Make these all ones, everything below and above the 1, 0. And then this is column C1, C2, and C3. So what would I do first? So we're basically trying to do RREF. Yeah, so what would I do first? I'd probably make this -2 into a 0. Right, so I would make this 2 to a -2 to a 0, and then make this 2 into a 0. So let's see. How would I make this -2 into a 0? So -2 is like technically row 2. And how I would do that is maybe add row 2 plus row 3. So row 2 plus row 3. And that'll give us your new row 2. So first number would be, what's first number in row 2? -2. Plus the first number in row 3 is 2. So that would be 0. Second number in row 2 is 5. Plus second number in row 3 is 5. That would be 10. Third number in row 2 is 0. Plus third number in row 3 is 8. 0 plus 8 is 8. And then third number in row 2 is 11. Plus third number in row 3 is -7. So 11 minus 7 is 4. Okay, and then we didn't mess with row 1 or row 3, so rewrite it. Okay, then what I would do is to get this 2 into 0, I would have to maybe multiply this by what? -2 by row 1. So row 3. Like, we'll give you row 3. So it would be -2 times 1 is -2 plus first number in row 3, that is 2, so that would be 0. And then -2 times 0 is 0 plus second number in row 3 is 5, so that would be 5. And then -2 times +2, that's -4, plus third number in row 3 is 8. 8 minus 4 is 4. And then -2 times row 1 is -5, plus third number in row 3 is -7. So that would +10 plus -7 is 8, 9, 10. That'd be 3. 6, 0, 10, 8, 4. And then I want to get these ones. I don't have to worry about that. But to save us more time, because I kind of did it already. To save us more time, you're going to get a matrix like this: 1, 0, 2, -5, and then this would be 0, 5, 4, 1, and then this would be 0, 0, 0, 2. So once you stop here, you can stop here because this would be false. So we said that the columns are C1, C2, C3. So what that means is C3 equals to 2. That's false. Or you get or 0 C3, which is really 0. So that's a false statement. 0 does not equal to 2. So this means so what they're asking, determine if vector V is a linear combination of vector A1, A2, and A3. Because of this inconsistent, because of this false statement, 0 does not equal to 2, so you could say no. Vector V is not a linear combination. Next one. Write a vector equation that is equivalent to the system. So they just want write a vector equation that is equivalent to the system. So what they want is they just want a vector equation, an augmented matrix. So let's go by columns. So let's start with the x1 column. So just use the coefficients. So go down vertically. So vector x1 has a coefficient of 4, and then this has a coefficient of 1, and 8. And then this one, x2 has a coefficient of 1, -7, 6. And the column x3 has a coefficients of 3, -2, and 5. And then we know that the equal sign is a straight line. So this would be 9 to 15. So write a vector. So this is not our answer. They want, so this is column x1, x2, x3. But they say write a vector equation that is equivalent to the system. So we need to find our linear combination. So our first linear combination would be x1, and we have 4, 1, 8, and then x2, and then this would be 1, -7, 6, and then x3 would be 3, -2, 5, and then that's going to equal to the vector 9, 2, 15. Uh, yeah, 9, 2, 15. Okay, so this is your answer. You're going to have to do matrices, or you're going to have to do RREF, right? To figure out what x1, x2, and x3 is. Okay, so they just wanted to set up like this, so this would be your answer. Okay, the next question says, write a system of equation for the equivalent vector equation. So they want a system equation. So it's kind of already all set up already. So all we got to do is FOIL out this x1. So this would be -2x1, and then this would be 3x1. And then if I let this x2, this would be 8x2 plus 5x2 equals to 0, so 0. So this is your system of equations. So this would be your answer. Okay, I am going to stop here and then we'll finish part 0 in another video.